We've covered the thermal expansion of solids and liquids, but we didn't talk about gases. To do that, we are going to look at something called the ideal gas law. Now, the ideal gas law should probably be called the ideal gas approximation. It is an approximation that relates pressure, volume, temperature, and the amount of gas in a area. I want to consider first what it means, or how this thing works, and then we'll talk about just what an ideal gas would look like. If I have a can, maybe, like this, this thing has a pretty consistent volume, right? The volume of this is going to stay the same. If I've got air particles in there, there is a certain volume, there is a certain temperature, there is a pressure, and there is a value n for number of particles in here. I want to see what happens under different conditions. Let's assume that our volume is going to stay steady. If our volume stays steady and we increase our temperature, these particles are going to be moving around faster. If we increase our temperature, we expect that the pressure is going to change, also is going to increase. In this case, we are holding our n, our number of particles in here, constant. So if we hold our number of particles in here constant, then an increase in temperature will cause an increase in pressure. What if we hold our volume constant and maybe our temperature constant also, but we increase the number of particles in here? Well, if we throw more particles in here, we're definitely going to get more pressure. So there's a relationship between pressure and number of particles. What happens if we keep our number of particles constant, and let's keep our temperature constant? We haven't done that combination yet. Then if I increase the volume of the container, I'm going to decrease the pressure. So there's a relation between all of these variables, and it looks like this. We are going to say the pressure times the volume is equal to the number of particles times a constant times the temperature. Now, we don't want to be messing around with negative temperatures or anything like that, so we keep our temperature in Kelvin. Pressure, this is in pascals, which are newtons per square meter. So we would like our volume to be in cubic meters. Now we need what this constant is and how that thing works. First, I guess I can say n, this is just a count. So maybe we've got 10 to the 12th atoms. Then it's just 10 to the 12th, right? It's a unitless number. So this is just call this a unitless count. So we need, what is this k? This k is something called the Boltzmann constant. And it has a value of 1.38 times 10 to the negative 23rd, and that is joules per Kelvin. It's joules because when we take a pressure and multiply it by a volume, we're getting a newtons per square meter times cubic meters is a newton times a meter, which is a joule. So the right side, we are going to need to come out to joules also. N doesn't have any units, so we've got temperature here in Kelvin times K has to come out to joules, so we've got to have joules per Kelvin. If you have taken Gen Chem, you would see a version of the ideal gas law that says PV equals nRT, and this is very closely related. When we do that one, we do pressure in atmospheres, we do volume in liters, temperature is still in Kelvin, but now this R value and the N value is a little different. N value is in moles, where 1 mole equals 6.02 times 10 to the 23rd. Pieces. You can think of a mole kind of like a dozen, right? It's not something that has its own inherent meaning, right? If you've got a dozen eggs, that's 12 eggs. If you've got a dozen marbles, that's 12 marbles. If you've got a mole of eggs, that's a 6 followed by 23 zeros. Eggs. If you've got a mole of marbles, it's a 6 followed by 23 zeros. Marbles. So it's a quantity like that. But it has a lot of meaning in chemistry specifically. This isn't a chemistry course, so I'm not going to spend too much time on that. But just so that you know that there is a relation between maybe an ideal gas law that you would have seen in a chemistry class and an ideal gas law that you would see in a physics class. And it really just is based on these kinds of units. We like to use newtons and square meters and cubic meters because in physics those are the kinds of units that are appropriate to the scale. If we're looking at a hot air balloon, we don't want to look at the volume of a hot air balloon in liters. That's a big number. We mess with it in cubic meters. All the other energy things that we do are in joules. So it would be nice to be able to use units that give us energy in joules so that we can relate it back to all those same things. But that's the idea of the ideal gas law. If we hold a couple of things constant in here, I'm going to move this over. If I've got P V equals N K T and I hold a couple of things constant, and maybe I'm just going to change pressure and N. So I'm going to hold volume and temperature constant. Then what I'm saying is if I increase the number of particles here on the right side of the equation, I must be increasing my pressure on the left side of the equation. That's kind of how you relate those back. So that's the ideal gas law. I do want to look at what constitutes an ideal gas. An ideal gas is one where the particles, the individual particles, have no volume. So we need particles have no volume. If I stick 12 atoms inside a 2-liter bottle, those atoms have no volume. It's not 100% accurate, but it's so close we wouldn't know the difference. So the particles have no volume. We need no intermolecular forces. So this thing works really well. No intermolecular forces. This thing works really well when we are dealing with a gas that is inert, right? This works well with like helium. It wouldn't work as well with water vapor, for example. Those are the big pieces that we need. Now this is not ever going to be the case, right? We can't have no intermolecular forces. We can't have particles with no volume. But we can get situations where this is a really good approximation. And that's what we're doing with the ideal gas law. We're not shooting for it to be perfect. We are just saying, if it were perfect, this is what we would get. And sometimes we're pretty close.